Hello guys. So waiting for more people to come in. Not sure if I can hear myself. Give me a second. Hello? Oh. That's right. Give me a second.
Alright, perfect. Now I can hear myself. Hello? Think it works now? Alright, perfect. Alright, welcome to the 10B LiveSolve. This will work very similar to the 10A LiveSolve. We will have 75 minutes. I'll be over here. Here's my workspace. So I can draw here, and then on the other side we'll have the problems. So when it's time to start, we will flip over the page and we'll start the questions. Okay. Just give me a second to figure out where the... Okay, it looks like... I see. So it's about there, like here. Alright, I was just figuring out where, like, the boundary is. It's about here, I think. Alright. Let me set up a 75-minute timer, and then we'll get right started. Alright. 1 hour 15 on the clock. We can wait for a couple more people, and then we're ready to begin. Alright. Looking good. Let's start. Timer started. Alright. Let's go. Number 1. 1013. That would just be B. So have them subtract 1. Number 2. 7, 8, 9, 10. That would be just 0. Because that's 8 times 9 times 10. Number 3, 7 pi. 7 pi is like 14159. So multiply that by 7 is like slightly less than 22, I think. So it's like 21 point something, like 21.9 something. So in this case, 2x, it's for 10. Plus or minus 10, and then 0 as well. So that would be E. A, B, C, D, E. Ball 1 is deposited in bin A, then 2 and 3 are in bin B. The next 3 balls are in C, then the next 4 and 5. Okay, let's first figure out which cycle it is. So 2024 is like 63 times 64 over 2. or that's 2016, and then plus 8. So we must have dumped 63 iterations before depositing the 2024 ball. After 63 iterations, we must have just finished putting things in C. So the next one would be in D. Number 5, Melanie changed some of the plus signs to minus signs. When the new expression was evaluated, it was negative. So obviously we want to make the largest numbers negative. What's the total value now? It's 50 squared, because there are 50 odd numbers there. And then we want to say that's 1250. And we want that to be, we want the sum of the first k to be less than 1250. So k squared less than 1250. K is like less than, or 1296 is 36 squared, 35. So we need basically 1 plus all the way to like 69 and then minus 71. So that would be how many of these? Well, it's 50 minus 35, so it's just 15. Let's just verify that. 28 over 2 plus 1, that's 15. Number 6. Integer side length in an area of 2024. Remember that is 2 cubed times something something. What is that? 8 times, I forgot again, 253. Okay, what is the least possible perimeter of the rectangle that is achieved when we get the most square-like shape? So that would be, I think that would be 46 by 44 for a perimeter of 180. Forty-five. Alright, what is the remainder when this is divided by 19? That would be 7 to the something multiplied by 1 plus 7 plus 49. So it's 0. Just verify that. 1 plus 7 squared can be written as, let's see, like 342 over 6, for example, 57. Yeah, that is divisible by 19. Number 8, the product of the positive integer divisors of 42. What is the units digit of n? It's how many of these? 2 times 3 times 7. So there are 8 divisors whose geometric mean is square root of 42. So it's 42 to the 4, which ends in 6. Okay. Let's move on to number 9. Real numbers a, b, and c of arithmetic mean 0. The arithmetic of these is 10. So we get a squared plus b squared plus c squared equals 30. And also a plus b plus c equals 0. So then there's square plus a squared plus b squared plus c squared plus 2 times ab plus whatever. So ab plus whatever is equal to negative 30 over 2, negative 15, which means the arithmetic mean is a. Number 10. Quadrilateral ABCD is a parallelogram and E is the midpoints. A, B, C, D. E is the midpoint of side AD. F is the intersection of lines EB and AC. Well, you see the lengths are in the ratio 2 to 1, so it's a 2 to 1 ratio there. What's the ratio of the area CDE F to the area of CFB? Okay, so let's say the area of ABCD is 1 to normalize. Then we know that the area of ADC is half, because it's half of the parallelogram. and AEF and BCF, let's call this area A, then this area will be 4A because the ratio of these are in 2 to 1. Actually, we know, like, for example, let's just turn it into a square because we can. It's a square, and we can see that we have, like, basically a unit square then. And so our shape looks like that now. So the height of this would be 1/3, and the width of this would be 1/2. This would be 1, and this would be 2/3, due to the similarity ratio, giving us an area of, this area would be 1/12. This area would be 1/3. This area would be 1/2 minus 1/12, which is 5/12. So the area would be 5/12 to 1/3, which is 5 to 4. And that would be A. Moving to 11, another geometry problem. WXYZ is a rectangle with WX is 4 and WZ is 8. Okay, 4 by 8, point M lies on that, so that's a right angle. The areas of triangles WX, draw my own version of this picture, more to scale hopefully, and we'll do it WXYZ, 4 and 8. We'll draw a right triangle. Such that WMA is right angle, WXM and WAZ are equal. Okay, let's see, what's the condition there? Well, if the areas are equal, then if this is A, then this must be 2A to make the areas equal. And then this would be 4 minus A, and this would be 8 minus 2A. And we know this is a right angle, so these two triangles, WXM and MYA are similar. So let's see, 4 over 2A equals 8 minus 2A over 4 minus A. In other words, 4 times 4 minus A. I guess we can write this as 2 over A to make it simpler. 8 minus 2A equals A times 8 minus 2A. This seems a little suspicious, but this seems correct so far. These cancel, A equals 1. So in other words, and we can just verify the geometry here, this length is 1 and this length is 2. And they both have area there. That looks about right. Let's see, this would be a 3, this would be a 6. And yeah, that would in fact be a right angle. We can even compute, this is root 65, this is root 45, and this is root 20. So that works out. And then the area of WMA would be 1/2 of, I guess we could do it by doing 32, which is the area of the entire rectangle, minus the areas of 4 and 9 of the bottom right. So that would give us 15. And that is answer C. And that was number 11. 12. A group of 100 students from different countries meet at a mathematics competition. Okay, the same number of languages, and for each pair they speak, and each pair of students speaks one language that the other student does not speak. So in other words, okay, let's see. Total number of languages. Okay, for example, what's the maximum number? Suppose that we have like, let's see, 4. Let's just do this simple example. We have 4 one language, and therefore each student has to speak some number of languages. And has to be like exactly 1. So actually we can accommodate 0 people with only 1 language satisfying this property. I guess 1, because we can have, if no pair of students exists, then we're fine. How about 2? Now I assume A and B have to be different, otherwise it would not be, that would be not well defined. So if you have 2 languages, then we need them both to speak exactly 1 language, and they need to be different, so that would give us 2 possibilities. Okay, I see. So basically the exclusion of the 2 has to be at least 2. So for every pair of students, then we can assign languages X and Y to that pair, so that every those are the 2 languages excluded. And so we know that if there are, okay, let's see, 3 students, then each pair of languages, let's see, then if everyone speaks 3 languages, then obviously impossible. Same with 0. If we notice that if we make everyone speak 1 language, then we can basically we get a maximum of n. If everyone speaks 2 languages, then we could have n choose 2, so long as no 2 are the same. No 2 pairs of languages are the same of each student. If we have 3 students speaking each language, then it would be n choose 3 and so on, right? So in other words, if everyone speaks the same number, yes, actually one would imply the other. In other words, if A speaks a language that B doesn't, then B must speak a language that A doesn't. So that just means that the sets of languages have to be different. So for example, if there are 9 languages, then we can accommodate for 9 choose 4 different students. I think the answer is just A. Because if we have 9 languages and each student speaks 4 languages, then we are guaranteed at least 126 possible students, such that this is satisfied for every pair of students. Basically, the smallest n such that there exists a k where n choose k is greater than or equal to 100, and that happens at 9. So the answer is A. Okay, positive integers x and y satisfy this. What's 1183? That's such a weird number. Well, it's not divisible by 2, 3, 5. It's divisible by 7. 1, 48, 6. Wait, is it? 63, 9. So it's 7 times 13 squared. And then, what's the minimum possible value of x and y? In this case, to minimize x and y, well, let's say we have we want to minimize u squared plus v squared. That would be at where x is like as big as possible, I think. No. We want them to be as, right, we want them to be as close as possible. Okay, so if we have root x plus root y equals root 1183, that's 13 root 7, then we need to have x plus y plus 2 root xy. That's one way to do it. We could subtract out x equals 1183 minus plus y minus 2 root 1183 root y. So this has to be an integer. Similarly, y equals 1183 plus x minus 2 root 1183 root x. So this has to be an integer. So in other words, x equals 7 times something squared, y equals 7 times something else squared, and so we get a plus b root 7 equals 13 root 7. Therefore, a plus b equals 13. The best we can do is a equals 6 and b equals 7. So the smallest possible value of x plus y is 6 squared plus 7 squared multiplied by 7. Which would be 85 times 7? 3649. And then multiply that by 7 is 595. Which is B. Okay. Moving on to number 14. A dartboard such that this... Okay, let's draw this out. So you have this dartboard. And then a target is the region where x squared plus y squared minus 25 all squared less than 49. Okay. Interesting. Wow, okay. This is just a geometry problem. So x squared plus y squared minus 25 is between negative 7 and 7. So x squared plus y squared is between 18 and 32. Those are nice numbers, because then we can say it looks like this. We have a circle here, and then a circle here. Where this length is 3 root 2, this is 5 root 2. And then, of course, the altitude to the side of the big square target would be, or the dartboard would be 4 root 2. So it would look like that. Suppose it lands in P. What's the probability that it lands in T also? Is just the area here that I'm shading here. Which seems like a weird region, but I think it's not too hard to actually calculate. The way to compute this is to draw extra radii. Always draw radii when you can. Remember that this outer region is 5 root 2. And we know that this height is 4 root 2, which makes this 3 root 2. So that is a 3, 4, 5 triangle there. And let's see. So that area can be computed as is m over n times pi. Stars on land. Hold on. We put something in B and then could be 32. Oh. Why would I say 5 root 2? Sorry, it's... Let me fix that. It looks like this. Okay, and then this is 4 root 2. This is 3 root 2. So the area in between there is 14 pi. 32 minus 18. And that's divided by the area of the entire... No, that's not 32. 64. No, 128, giving 7 over 64 pi, giving the answer 73. Let's see, just double checking. 8 squared times 2. Therefore, that would be 7 pi over 64. Yeah, 7 pi over 32 would make no sense. That area is too small for that to be that big. Moving on to number 15. A list of 9 real numbers consists of that. 1, 2.2, 3.2, 5.2, 6.2, 7, x, y, z. That's a total of 9 points. The range is 7, so z equals 8 immediately. And the mean and median are both positive integers. How many ordered triples are possible? So I believe z has to be 8. Actually, no, z could also be equal to -1. So that is also not true. Hold on. Okay. So let's take it one by one. Z could equal 8. There's case 1. It could also be z is between 7 and 8, and x equals z minus 8, or 7. The range is 7. And then, or z is, x is -1, or 0. Z is less than or equal to 7. And I think those are the only cases that we need to worry about. So let's take a look. Z equals 8. The median has to be an integer out of the 9, so either x or y is the median. So, and then x, let's first compute the sum of these 6 numbers, which is 1, 2, 3, 5, 6, 7, 6, 12, 17, 24.8 plus x plus y plus 8 over 9 is an integer. 32.8. Let's see, what else do we have about x, y, z? Okay, yeah. So x plus y is like, this is like 32.8. So the next possible number, since x is greater than or equal to 1, x and y are both positive. In this case, 4.8, no, sorry, 3.2, 12.2, and so on. I guess 19.2 or 20.2, but we can see that this is not possible because x and y are less than or equal to 8. So these are the only possibilities. Furthermore, x or y is an integer. So if x plus y is 3.2, then you could do like 1 and then 2.2, but then that would not make the that could not possibly make the median an integer, because right now the median is 6, like there. So either, like if I make the numbers really big, or I guess the biggest it can possibly be, 1, 2, 3, 4, 5, the median would be 3.2 in that case, which is not good. So this is not possible. Or the median is, okay, so x plus y is 12.2, then, and z is 8, so y is less than or equal to 8, x is greater than or equal to 4.2, right? So 4.2, 8 is the most extreme that we have. But that wouldn't work, because 1, 2, 3, 4, 5, the median would be 4.2 and then another 8. So the median would be 5.2 there. So x has to be greater than 5.2, and it has to be an integer. But it's also less than 6. So then x has to equal 6, and y equals 6.2. And I think that works. So this gives us one possibility. 1, 2.2, 3.2, 5.2, 6, 6.2, 6.2, 7, 8. Let's see, z is between 7 and 8, x is between, I guess, 0 and 1. They're offset by the same amount, and then, of course, in that case, y would have to be the median, because x lies here, and z lies there, so y has to be between 3.2 and 5.2. Furthermore, it's an integer, so y is an integer, so it's either 4 or 5. And then let's see, z is that and that. So let's say z and then z minus 7. So if y equals 4, then the total sum of the known values would be 1, 3.2, 6.4, 11.6, 17.8, 17.8, 24.8. Yeah, so the sum here is 24.8. Remember that. And then we can add 4 to that, so 32.8. So then the total there, we have 9 numbers. So the total would be, had to be like 36. In this case, the total has to be between, or x plus z would have to be either, it's between, strictly between 9 and 7. So in this case, we would, let's see, 45. Yeah, so that's not possible. And then y equals 5, I think, is also not good for a similar reason. Because the sum has to be between 7 and 9, that doesn't give enough room. So I don't think there's any cases here. How about x is 0? So it's 0, 1, 2.2, 3.2, 5.2, 6.2, then 7. And then z is somewhere here. The sum now would be similarly 24.8. Let's see, 20 minus 24. Yep. And then z has to be somewhere there, and then once so z could be as small as you like, but y plus z has to equal, once again, or in this case, 2.2, 11.2, or 20.2. This is not possible because z is less than 57. This maybe is possible if y and z are very small. But that would make the median not. So if they're very small, then the median would be 2.2, I think. So that's not possible. So it's only possible if they're sum to 11.2. So, and z is greater. So like, one of them has to be. So if they're two numbers, then we know z is at least 5.6. So z is definitely not the median. So y has to be the median. Z is at most 5.6. So y would have to lie 0, 1, 2, 3, 4. So this would be where 2, 3, 4. And then y has to be there. So y has to be between there again. 4 and 5 again. 4, 7.2. 5, 6.2. So 4, 7.2 doesn't work because z is too big. So 5, 6.2 is the only possibility. Then we have the two possibilities here. X, Y, Z here is, what is it? What is happening? Where did I put my value here? Oh, here. So the two possible values would be 6, 6.2, 8, and 5, 6.2, or sorry, 156.2. 056.2. Let's verify 11.2, 12.2 plus 8. Yeah. Okay, cool. So the answer here would be probably B. Number 16, Jerry likes to play with numbers. You roll the numbers 1 to 2024 on the board. 4 numbers, erase them, replace them either their sum or their product. For example, 1, 2, 3, 4, either 11 or 30. After repeatedly performing, all the remaining numbers on the whiteboard were odd. What is the maximum possible integers on the whiteboard at that time? Okay, let's see. The number of odd integers here would not be, okay, would it be decreasing? Like, for example, if you have 4 even numbers, then you definitely make an even number. 3 even numbers and an odd number, then you could have either another, like one, you can have at most 1 odd number. So the sum always decreases the number of odd numbers. And the product always also decreases. So we know that the maximum, well, there's 1,012 odd numbers to begin with, and we never get any more. So the answer is at most 1012. So basically, there's a bunch of like even numbers that don't affect anything. So we can just combine them. Like basically, we can just say like we have infinitely many even numbers, and we can see like what's the like. Okay. How do we like get rid of all the even numbers? We can, there are 10, 12 even numbers. We can get rid of all of them by basically taking them out one by one. That reduces the number of even numbers by 3 every time we do it. So we end up with, I think, exactly one even number at the end. And then, like, okay, let me just do a table here. Even, odd, even, odd, even, odd, and odd. For the sum, that would be even, odd, even. And for the product, that would be even, odd. You can see that the total number of odd numbers decreases by 3 here, by 2 here, by 2 here. Or sorry, I think we subtracted by 1 in this case, or 2, yeah. So minus 3 if we pick this. Otherwise, they're both even, so we're sad. So we lose 2 here. We lose 0 actually in this case. And then we also lose 0 in this case. So these are the 2 that are like not lossy in terms of odds. In other words, we can take out 3 evens by taking the sum of 3 evens and an odd, but we'll still be left with at least 1 even number, right? So that's sort of like a slight problem. So instead, okay. So we can either, the total number of evens or odds decreased, the total number of numbers, of course, decreases by 3 every time. So when we get to 10, 12, I guess when we subtract things out, we're going to eventually reach 10, 13 integers, which means that there's so there's 10, 13 integers after doing this step some number of times, and we can quickly see that there's still at least 1 even. So we need to do it at least one more time, where there's 10 integers, and one of them's 0 or even. So we have a maximum of 10 numbers when there are no more even numbers. So our answer is just A, and we can prove by construction. We just do this one here. We convert, this one here, where we take the remaining even number and then turn it into an odd number there, reducing the number of odds by just 2, giving us 10. Okay. 17. Race among 5 snails. There's at most one tie, but that tie can involve any number of snails. How many different results of the race are possible? Okay. Let's see. Yeah, sure. So let's do casework on like what that tie is specifically. So that tie could be like all 5 of them, which gives us one possibility. They're all tied for first, I guess. If it's 4, then there's 4 tied and then 1 individual. So that gives us 2 possible ways to order them, multiplied by, I guess, 5 choose 4 ways to pick the group of ties. So that gives us 10. If there's 3 people tied, then it's 3 factorial ways to order, and 5 choose 3, so that's 60. 2 ways, which would be 2 factorial times 5 choose 2, or 4 factorial times 5 choose 240. 1, 5 factorial times 5 choose, in this case, it's just 5 factorial, because we're not choosing any tie. Wait. Yeah, if the tie involves 1, then that just basically means 0 tie. So the total here is 360, 420, 431. D, I'm like not, I'll put a star here because I'm not super convinced, but we'll just move on. How many different remainders can result in the 100th power divided by 125? Just 2, because it's either 0 or, actually wait. If it's a multiple of 5, then obviously it's like 0. Otherwise, it's going to be 1 because it's relatively prime to, if it's relatively prime to 125, in other words, not a multiple of 5, then the power would give us 1 by Euler's formula. Phi of 125 is exactly 100. So in fact, the answer is B. And I don't think there's any trickery with negative integers, so I think we're good. It's either 0 or 1. Possible, okay. Okay, so non-vertical line contain this this number of lattice points. We know that no line can contain exactly 2 lattice points, so that's definitely no. That's definitely no. 1 and 0. 0 slope, non-zero rational, and irrational. Okay. Yeah, something with 0 slope can definitely pass through 0 lattice points. It can't pass through exactly 1, and it can pass through infinitely many, so that's good. If a rational slope similarly can pass through 0 points, it cannot pass through exactly 1 point, and it can pass through infinitely many. All of these, let's see. Irrational slope can pass through that. Irrational slopes can pass through exactly 1. Basically, like, EX plus pi is never gonna be an integer, right? So we're happy with that. But also, we can make it like this one's like EX, for example. And then greater than 2 points, can it? No, because if it contains two points, then the slope has to be rational, so this is not. So there's a total of 1, 2, 3, 4, 5, 6. B. Nope, C. It's not Miss Bubble here. Okay, number 20. 3 different pairs of shoes are placed in a row so that no left shoe is next to a right shoe from a different pair. Okay, so the 2 possibilities are 2 left shoes, or left, right, and that forms a pair. Right, the only impossibility is, I guess we can also have two right shoes, as long as the ones that are left and right are in fact pairs. So we can do casework. It's the same thing, right? Where we can have 0 pairs of left and right, in which case that's not possible. In fact, the number of left-right pairs has to be at least one. It has to be odd for there to be left, and right. So left, right, and then 2 lefts and 2 rights. This one has, there's 5 ways to pick the pair multiplied by 3. I don't know why I saw 5, sorry. So it's either one or all of them. So left, left, and right. In that case, there's just 3 ways to pair them. Wait, I'm confused. Oh, okay. It's a row, not pairing. Okay, right. So what are the possibilities? Like we have, like for example, can we ever have the pattern RLR? No, because this pair or this pair is not matching, which would be very bad. So therefore, we similarly cannot have RLR due to the same issue. So that means that we can never have this pattern LRL. So every right has to be next to at most 1 left. Similarly, every left has to be next to at most 1 right. So for example, like L L L R R R R R R L L L. What else is possible? Because if we have an RL, then it has to look like RRLL, right? And similarly, if we have LLRR. So I guess there's this case. There's the... We know that there exists an RL or LR somewhere. So let me just write these. RRLL, and then LR is possible, or RL. No, actually that's not possible. And then similarly, RLLL, RR, and then the inverses, right? So LLRRR, LRRR, LL. All of these work, right? Or could work. I guess we haven't confirmed. These are like the middle positions. We can have RLLRRL, and I believe that's it. 1, 2, 3, 4. If we have LLRR in the middle, then there's 2 possibilities. There. And then otherwise there's only 1 on either edge. Okay, cool. So in this case, all we have is that these have to be 1 pair, so there's 3 ways to pick that pair, and then 2 ways to arrange the other ones. In this case, again, similarly, this is 12. In this case, these have to be the same pair, these have to be the same pair, and these have to be the same pair. Similarly, these have to be the same pair, and so on. So that just gives us 3 factorial, right? Just 6 ways to arrange those right shoes, and then the left shoes become obvious. Similarly, this is 6. In this case, we need these to be the same pair, and these to be a pair, and these to be a pair. So, and then all of these are symmetric, right? So actually, we can treat these will all have the same number. So, in that case, then we have basically 3 factorial times 2. 3 factorial ways to pick, for example, the order of the right shoes. And then that actually uniquely determines the order of the left shoes. Wait. If we determine the right, sorry, it's just 3 factorial. Because after picking the 3 factorial ways to order the right shoes, the left shoes become obvious. Okay, agree. So the answer is just 12 plus 12 plus 6 plus 6 plus 6 plus 6 plus 6 plus 6. That's 36 plus 24. That's 60. A. We'll come back to this one as well, if we can. Number 21. Two straight pipes. So you have this and this. This is flat 4. Some of the possible radii of a third parallel pipe lying on the same floor and not in contact with both. Okay. So there's only two possible such pipes. We can have this pipe, and I think that's it. Because everything else, to be in contact with this pipe would... Let's see, lying on the same floor, so that, yeah, I believe that's it. So then, okay, so then, what is this? 1/4, 5/4, 3/4, and this length would be 1. So let's enlarge that. 3/4, 1/4, 1, 5/4, 1/4. And the center of the circle is basically here. Let's call it R. And then we have basically 1 plus R, 1. So it's 1 plus R and then 1 minus R. So this is 2 roots. What is it? If you have like this, and it's like 1 plus R, and it's like 1 minus R, then this is root 4R. 2 root R, and then this is root R. Because it's 1/4 plus R, 1/4 minus R. So, yeah, that would be root R. So 3 root R equals 1, R equals 1/9. And then for the larger one, that would be R plus 1, R minus 1. So this would be 2 root R, and this length would be R minus 1/4, R plus 1/4, so root R. So then root R would equal this length, which is 1. So R equals 1. So in other words, it would like be the same size as that, which I think makes sense. So the sum of the possible values is 10/9. The other answer choices are scaring me, but I think the answer is just C. Because what if there's another possible pipe of... I'm not convinced again, because there could be multiple. Like, a parallel pipe means that Okay, yeah, we'll come back again. Number 22, a group of 16 people, this many indistinguishable committees. Each committee will have one chairperson and one secretary. Number of different ways to make these assignments. Okay, yeah, so what is it? 16 factorial times 4 factorial, 4 factorial, 4 factorial, 4 factorial, divided by additional 4 factorial, I think Because imagine if you label them 4A's, 4B's, 4B's, 4D's, but then they actually have to be indistinguishable, so you divide by 4 factorial, multiplied by whatever the number of ways to pick a chairperson and a secretary, 4 times 3. So this gives us 3 to the 4. This gives us, well, this gives us 3 to the 6 times something. Each of these is like 3 to the 1, so that gives us 3 to the 1. So that just gives us 3 to the 5. Come to check back this one as well. 23, or 24. Oh, no, 23. Okay. Right, okay. Okay. Yep. Let this, how many of the values, this, and this are in integers? Let's see. Well, obviously, let's see. If it's even, then yes. Let's see, 1/2. Is negative 1 a root of this? Negative 1/2 plus 1/4 plus 1/8 plus 1/8. Yeah, it is. Maybe it's a double root? It's like m plus 1 multiplied by like something. I'm kind of scared. Okay, anyway, the even ones are definitely true, right? Those are definitely integers. So the only ones that are worrisome are 2023, 2025. So 2023, that gives us 1/2. Yeah, so notice how if m plus 1 is a divisor, then this looks like, so it's like 1/8 multiplied by some integer polynomial, and m plus 1 is a factor of this. So we know that this is some integer polynomial. So 2023 is definitely divisible, but because 2023 plus 1 over 8 is an integer. 2025, I'm not sure about that. 2025 is 1 mod 8. So that would give us 1/2. The fractional parts would be 1/2. And then when you square it, it becomes, it's always going to be 1 mod 8. So it's going to be 1/2 plus 1/4 plus 1/8 plus 1/8. So that gives us yes. And then it would be like, similarly for 2023, it would be, I see. Like if you add 1 to P of M, or if you subtract 1 from P of M, it becomes divisible by M minus 1. So this looks good. Yeah, all of them are going to be integers. 25. Okay. And 2 by 2 by 7 block. 1 minute, one unit deeper. This is just a system of equations, right? Can you just say like 3a plus 1 equals 2b, 7a plus 1, sorry, 3c plus 1 equals 7a, and finally 3b plus 1 equals 2c, and then we just solve. Like, let's see, for example, b equals 3a plus 1 over 2. Let's plug that in. 9a plus 3 over 2 plus 1 equals 2c. Multiply that by 2. 9a plus 5 equals 4c. And we also know 3c plus 1 equals 7a. Let's just multiply this by 7. 63a plus 35 equals 28c. This is 27c plus 9 plus 35 equals 28c. C equals 44. B equals 29. A equals 3c plus 1 is 133 divided by 7 is 19. Let's just double check. 19, yep, everything works. What is the value of A plus B plus C? That is just 48 plus 44 is 92. And that is E. Okay. Cool. 20 minutes, 18 minutes to check is pretty good. Let's go back to the starred problems real quick. So number 23, I'm a little worried about. Oh, wait, I just skipped one. Sorry, this is 24. No, this is 22. So I missed 23. I see. So let's do one more. Fibonacci numbers are this. What is this? Plus this, plus this, plus this. This looks like a basic induction problem. Let's see. So F2, what is it? So 1, 1, 2, 3, 5. I guess. And then, what are the 2, 4, 6? So it'd be 1 plus 3 plus 5 plus 8. Sorry, 1, 3, 8. 21. So this is the Lucas sequence, I think. 1, 3, 4, 7. 11, and so on. So that does seem to fit. Is there a nice form for the sum there? Let's see. 1 plus 3 plus 4 plus 7 is 15. Plus 11 is 26. So it's 1, 4, 7, or sorry, 1, 4, 8, 15, 26. So I guess there's no like easy formula, but it's not too bad to just compute it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 4, 8, 15, 26, 44. So I think it's just add the 2 and then subtract 3. So 44, 70. Oh yeah, it would just be, sorry, you can see. So that would add up to 73, so it'd be that minus. So some first would be that, and then the next one would be 120, and the next one would be 199 here, and 322. So the next one would be 120, then the next one would be 196, then finally 319 is B. Just double check. 1, 3, 4, 7, 11, 18, 19, 7, 6, 3, 9, 2. Okay, yeah, and it ends in 9, so I think I'm pretty confident about that one. Alright, 15 minutes left. Time to build stuff, time to check stuff. Okay, I'm gonna figure out what's happening with number 22, or 21. Wait, what? This is 22. 22, let's see, 4 instructional Seems right. We're overcounting by 4 factorial. So it's 16 factorial over 4 factorial to the 5th. That makes sense. 4 factorial to the 5th is divided by 3 to the 5. 16 factorial is 3 to the 5. So there's 5 multiples of 3 and then 1 multiple of 9. So that gives us 6. So 6 minus 5 is 1. And then, of course, the number of ways to make chairperson and secretary within each committee, 4 times 3. So that gives us 1 for each committee. So that's 4 plus 1 gives us an answer of 5. Okay, cool. I think I checked this one. Number 21, I'm like gonna think long and hard about possible edge cases. Because if it's 1/9 and 1, I'm not entirely sure why, for example, like D exists. Like that kind of suggests that there's another circle of radius 1/9 that can do this. I don't think so, because unless there's something like really dumb, I don't think this is possible. Like I assume in contact means like I assume the pipes are like considered to be infinitely long, so it just reduces down to the 2D case. Otherwise, there's like a really strange thing going on here. 1/9, definitely like under both and then on top of both. I don't think one can be like under and then the other one. It just doesn't work, right? These arcs don't intersect, these don't either. So yeah, so I think it's just 10/9. I'm like if you have two circles of radius 1 and you drew this, then the radius would be just 1/4, right? 1/4, that would make this 5/4, that would make this 3/4, and that would make that 1. Okay, yeah, that seems right. So that would be like this circle here. Or, right, the other circle. Okay. So I think that's good. 10/9. Seems good. Number 20. Left and right shoes definitely needs to be checked. As we stated before, since there exists an RL somewhere, or an LR, then we know that the pattern RRLL or LLRR exists. So for example, we can place it in the middle, which would give us two possibilities, LLRR and then L then R, or R then L, so LLLRRR or RLLRRL. Similarly, we can have RRLL and have those two possibilities, or we can have RRLL at the start, RRLL at the end, LLRR at the end, or LLRR at the start, and each of these only has one possibility, because if we did RRLL then we would end with LRL, which would make it impossible to win. So in this case, yeah, so in this case, if we have 6 shoes lined up like this, these are the only 8 possible cases. 3 times 2 squared, because we need to pick which pair to represent in the middle. And then there's still like, we can order the remaining shoes however we want. So there's 2 ways to order the right shoes. So for example, 3 factorial ways to order the right shoes, and then 2 remaining ways to order the left shoes, because we can swap them freely. We can say 3 right shoes, and then, or sorry, you put the 3 right shoes there, and it's the same. If you put 3 right shoes here, then that uniquely determines which shoes are in the left shoes, so that's 6. Same for this one. And same for this one. And same for that one, and that one, and that one. So they're all symmetric, right? No left shoe is next to a right shoe from a different pair. So if a left shoe is next to a right shoe, it must be from the same pair. In other words, every left and right shoe together must be the same pair. Right, okay. So I think I've understood this enough. So there's 12 in the first two cases and 6 in the remaining, so it's like 48 feels like 12 extra. Yeah, okay. Let's double check number 18 or 19. Zero slope. I can either pass through 0 or infinitely many and nothing in between. Check x, x, check. If it's rational, then it can pass through 0 or infinitely many, nothing in between. Because it passes through 1, then it passes through infinitely many. Like, for example, if the slope is like 1/5, then it passes through 1, then it passes through infinitely many. But if it doesn't pass through, it can pass through none as well. Like, for example, 1/5 x plus pi. And then, okay, so that could be 0 or infinitely many. Finally, irrational numbers. Ex plus pi is an example that passes through exactly 0 because there's no x that makes it an integer. Otherwise, the ratio, what is it? Like pi can be expressed. Like, what's the rationale? Like, okay. We can figure out that out after a test, but I'm sure there's no integers such that e plus pi is b, right? So, and then you can also have ex plus 0, and that passes through only the origin. And then exactly 2, not possible. Every time it passes through, some linear combination also exists, so it's never exactly 2. And then more than 2, similarly, if it passes through 2, then it cannot pass through more than 2. More than 2 implies infinitely many, which would imply a rational slope. Okay, so this looks correct. 6 minutes. I guess I have this starred, number 17. So I think the reason I'm like a little concerned about 17 is the fact that there's no like one case. So if there's only, okay, there's at most one tie. So there's no tie, or there is a tie. And if there's a tie, then it's between at least 2 people. So I think that's a good rationalization. So case 1 is like no tie. If there's no tie, then it's just a standard 5 factorial number of ways to arrange the placements. I agree. If there's a tie of 2, then it's equivalent to having, first of all, we have to pick which subset of them are tied, and then it would be the same as rearranging them. Seems fine. That seems fine. That seems fine. Yep. 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 Okay, I agree. Let's move on. Okay, this one I think I'm pretty confident in. There are 24 numbers, and we always subtract the number by 3. So if there's that, by the pigeonhole principle, there cannot be 13 numbers left. So the maximum would be 10, which is also the smallest answer choice, which confirms our suspicion. Number 15, we need to check. I'm not very... Okay, the median has to be one of the elements of the list because the number of elements is odd. So we know that either x, y, or z is an integer. X, y, and z, right? Okay, right. So either the outer bounds are either x and z, x and 7, and or y and z. So if z is 8, then x is at least 1. This has to be an integer. Sure. So then x plus y is like this, but that doesn't work because that would make 3.2 the mean. So the number between 3.2 and 5.2, 6, 6.2, and 8 works, where x is the mean of 6. The other one where it's 5, 7.2, would not work. It has to be at least 5.2. In fact, right, so this is the only possibility. If it's 7, that's not possible. 8. I just make sure that both of these actually work. So 6 would be here, 6.2 would be here, and 8 would be here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or sorry, 6, 7, 8, 9. That works. And then the mean, just add point, what is it, 6, so it's 24.8 plus, I just make sure that that sum is correct. 1, 2, 3, 5 adds up to 11, plus 6 plus 7 is 24.8. Okay, 24.8 plus, what is it, 6, 6.28, 20.2 adds up to 45. Okay, that works. And then we just need to check this case I'm pretty sure is true. So x is between like 0 and 1. Z is between 7 and 8. And finally, y would have to be between 3.2 and 5.2. So it's either 4 or 5. So the minimum sum is like 24.8 plus 0 plus 4 plus 7. So 35.8. Oh. Wait. It's possible? Am I bad? Hold on. It's like 4 and then 24 point. If y equals 4. Oh wow. 7 y 1 minute, 7z is 8. So I think like 0.1, 7.1, 24.8, and then the number in the middle is 2, 3, 4. That gives us 11.2. Adds up to 36, so that works. And then 30 seconds. If it's 5, then it doesn't work, because these would have to subtract by 0.5, in which case it doesn't work. Okay, I'm not sure why I just like didn't count that. I mean, unless I'm... Oh, is it 28? No, it's 24.8. What? It should be 28.8. Yeah, I think I'm just... Okay, so there's one extra case. So the answer is actually 3. Okay, I mean, I think, I don't think I made any other mistakes. Okay. Whoop. Alright, I guess, okay, I might have changed it to the wrong answer, but I think that last one does work. So I think I caught that one in time. Oh, like, what is happening here? Why did I say 32.8? It's obviously 24.8. And if y is like 4, then it like makes sense. Okay, cool. Sick. Let us take a look at the answer key. B, B, E, D, B, B, A, D, A, A, C, A, B, B. Oh, what's happening here? Did I miss bubble, bro? No, I just did 4. I just did 7 plus 64 wrong? Okay, that's my fault. Okay, 15 was in fact C. Caught that one. Okay, that is actually my most embarrassing mistake so far, ever. 16 is A. Okay, where are we? C, A, B. Nope. What, 17? Oh, 17 is here. Is here D, B, 19, C, A, C, A, B, E. Dude, that is really embarrassing. 7 over 64 adds up to 73. Okay, well, that's my only silly. Very frustrating 144. Always happens, huh? Alright. Yeah. 64 plus 70. 7 is 71. Bruh. Okay, I think everything else is good, so I got a 144. Final score. That last minute, like, just figuring out that one problem very quickly, it was like, nice. Okay. Nice. 144. Yeah. So this is why it's always good to check your answers. If I had like 30 more seconds, I probably would have also checked the problem right above number 15. I like what? I don't know how to explain this. I don't know what made me think. I guess so. One thing that could explain is like I like looked at the answers too early, and then I saw 73, and I was like, okay, adding them up, and I prematurely like put 73 because it was like the middle answer or something. Yeah. I also thought square root of 35 was 5 root 2. Maybe because 32 is 2 to the 5, and then that got me confused. But yeah, that was also embarrassing. Like, what is this? Definitely made a couple sillies. I guess that first mistake got me there. But yeah, I'm not like angry. I'm angry at myself for this one silly, but it was made up for by this detecting the other silly. I guess, yeah. I think this problem set was actually like significantly easier than a normal 10, AMC 10. This was like, if you look at the later problems, right? Like, this one is pretty doable for anyone who's taking like Algebra 2. This was very difficult. Number 21 is actually a very stock problem. Like, if you've done enough circle problems, that's like pretty simple. And then number 22 is also like pretty easy, right? Like if you're already 90% there by just doing the counting, which is like a very simple constructive like counting problem. Like, I'm not saying it's easy objectively. I'm saying it's easier than like a normal number 22 would be on average, which I was really surprised by. Similarly, number 23 is very guessable if you just compute the first few values. Number 24 was I was really surprised to see this one, because this is just modular arithmetic, right? Or just like figuring out, like you can even just bash it out and compute like the fractional parts. There's so many different avenues that all work. And then 25 maybe might have been like super surprising. I guess like it's on the last page, and it's like alone, and it's like a big problem, but It's literally just a system of 3 equations. So this one is very doable if you have more time. This is also why I recommend that you like scan the problems before you do them. Like look ahead and see like which ones you can do. This one, like, this is not only a fun looking problem, it's also like pretty easy just to do, right? It's just a system of 3 equations, and it's actually very nice because each equation only involves 2 variables. So this is not too hard to actually just solve on its own, right? I guess it's a little bit weird because there's like big numbers, but if you just do like substitution or elimination, it should be pretty straightforward. Just don't overthink it, right? If you can solve it by solving a system of 3 equations and 3 unknowns, then just do it. Probably won't take you more than 5 minutes. Yeah, so definitely look forward. Number 20 was one of the hardest problems on the test. Like, actually, I think by far. Like, there's no other problem that made it that was like remotely close to this one in difficulty. This one requires a lot of like quick thinking of like, okay, like making the observation that you have to have a right left or a left right somewhere, maybe not too bad, but then like building off of that. Like I know like I was considering like just listing out all the possible ways in a less like smart way. Like if you realize that there's some LLRR or RRLL sequence in there somewhere, then you should be just good. The rest kind of falls into place from there because there's only like there's only like 6 ways to put an LLR or RR or RRLL, what a tongue twister, in your sequence of 6, and then there's only 2 ways to fill in the remaining 2 because one of them's a left and one of them's a right. So actually systematically you can already just figure out that there are a maximum of 12 possible sequences that you can have, and 4 of those don't even work because you end up with an RLR at one of the ends, or LRL. So yeah, so we end up with this one was definitely the most involved, I think. There were definitely other questions that took a lot of time. This evens and odds question was one of them, but I think even if you do like a greedy approach of like removing as few odds as possible, like you're bound to hit 1010, right? In fact, it turns out that as long as you're like removing evens at every step, like at some point everything's an odd, and since like this problem is posed as one of those like invariant questions where, for example, if you have like a bunch of numbers on the whiteboard and then you like replace a bunch like 2 numbers with their sum, you might have heard of like the invariant is the sum of all the numbers on the board, because when you replace 2 numbers with their sum, the sum of all the numbers on the board doesn't actually change. Similarly, if you replace them by the product of the numbers won't change, right? So that can be like a super useful invariant. For example, in this question, if you could only choose 4 numbers and add them up and replace the 4 numbers with their sum, and it asks like, okay, at some point there's only 1 number left. What is that? What is that number? In this case, that's actually not possible, but you get the idea, right? So the sum would just be the final number would just equal to the sum of the original numbers. In this case, the invariant is actually a lot simpler. It's just the number of like numbers on the board. It's not really an invariant because it changes, but it changes like predictably. This is what we call a monovariant, where the number steadily like decreases or increases. In this case, it decreases by exactly 3 every move, regardless of whether we replace by a sum or product, because we're replacing 4 numbers with just 1. So if we're reducing the number by 3, we just end up with like every operation we're subtracting the number of numbers by 3. So you start at 2024, then you go to 2021, then 2018, then 2015, and so on. until you reach a number where like it is plausible that all the numbers are odd. Since there are 1012 even numbers to erase, we need to remove at least 1012 numbers, right? Most of which are going to be even. Which tells us that actually, like the maximum possible is just if we subtract 3 until we reach a number under less than or equal to 1012, which gives us our answer of A. And actually we can generate an example of doing that, like reaching 1010 odd numbers only, relatively easily, right? We can like reduce all the even numbers down by combining them repeatedly until we get only one even number, and then we replace that even number with 3 other odd numbers with a single odd number by adding them. In which case we have lost basically like 2 odd numbers in total. So that gives us A. So this was definitely a very standout question for me. This is like one of the more, I think, interesting problems, and also like a problem that doesn't generally appear on a test. Number 17 was also one of those questions, but it was like, I think if you are comfortable with doing casework, it's also not too difficult to figure out. Maybe like it might trip you up that the actual tie is not actually ordered. In other words, the order of, in this example, Abby, Cyrus, and Elroy are tied for second. It doesn't matter how they're arranged. So that gives you like a different, that's slightly, that is a slightly trippy part, that you would get a different answer if you didn't do that, right? So for example, if the ties were distinguishable, then, right, for example, let's take a look. Yes, Richard, exactly, right? The number of numbers is always 2 mod 3, and that's the invariant that I was talking about earlier, right? Since we're subtracting 3 numbers each time, I guess the invariant would be the value of the total number of numbers on the whiteboard modulo 3, and that's always going to be 2. Yeah, so that's another way to describe it. Yeah, so the answer is A or D. D is definitely impossible because we can't have more than 10, 12 odd numbers on the board ever. Oh, actually, that is something I need to clarify, right? That I actually immediately jumped to is that in this table we never end up with more odds, right? And in fact, we never end up with more. I guess there's this one case where we do add one even, but the key is that the number of odds will never increase. So the answer is going to be that is actually important, right? But yeah, with that observation, you can quickly see that the answer is A. Back to number 17. Here, if we said, let me just have some work on the bottom. If we said ties were distinguishable, then actually it would be equivalent to like figuring out the overall placements and then picking a group of consecutive entrants to be basically forming the tie, right? For example, how many ways there can be no ties? There can be this pair of ties, this pair of ties, this pair of ties, this pair of ties, this trio of ties, right? So there's 4 different ways to pick 2 people to be tied, 3 ways to pick 3 people to be tied, ABC, BCD, or CDE. 2 ways to pick 4 people to be tied, and then 1 for all of them to be tied, right? And then also there's one extra case where none of them are tied, and then you multiply that by like 5 factorial, and that would be the answer if like the tie, for example, like within the tie there was like a tiebreaker that further induced an ordering of the tied players, right? Because that would actually be equivalent to figuring out the placements first and then determining which group of people tied. And so this would be the alternate answer. I guess it would be 1320 in this case, which is not an answer choice. So actually, you can figure out that that reasoning is incorrect. 96 on the 10. Yeah, I mean on the 10 I think it's like not sure, like I would give it like a slightly less than 50%. I'm but you know, don't take my word for it because I haven't taken like I haven't looked at the cutoff scores or anything for the past 3 years. Just based on like the quick like investigation I did for last stream where I looked at the cutoffs, historical cutoffs. It looks like they're relative to the difficulty of the test, they're actually making it easier to qualify for the AME. But I would have no idea, or I would have no way to actually know. But yeah, I think you have a chance to qualify. It's definitely not like it's not guaranteed. That's all I'm gonna say. And I don't know if I'm like a super reputable source for like actually determining the cutoff. Like if I had to guess though, what was is the 10A cutoff? Is there like an idea of what that was? That's yeah, so we don't know. But like for example, the 10A from last year was 103.5. For this test, I think because it was like much easier than the A, in my opinion. Like actually much easier. I think I would put it at like about 105 to 110. But we'll see. Like it depends, right? If this test is more sillyable than the A, maybe the cutoff actually will decrease, right? Though I don't see many like situations where it's like a super tricky question, right? Like for example, the singular silly that I made was like an addition error, which is not systematic, right? Everyone else probably did not make the same mistake as me, or at least a good portion actually added correctly. So I think I would, for this entire test, I would rate the difficulty. If last week's AMC was a 4, then I would call this like a 3, maybe slightly less. Like a 3 would be a good out of 5. And then the trickiness would be pretty low, like 2. So with that in mind, I think the cutoff is going to be on the higher side. But yeah, I mean, again, you shouldn't beat yourself up over your score. Like given that you took the 10, I already know that you have at least 2 more years to take, more AMCs. So obviously there's no rush. There's not really much you could have done better on the test so long as you think you did your best. So really, like this, don't be results oriented. Don't think about the score too much. Just aim to improve, because that is what will maximize your score in the future. But yeah, are there any like questions about like, do you want to go over a specific question? And if not, I think we can just end it here. I think if you just search up 2024 AMC 10B answer key, you should just get the answer. Like, I think it's the second link. Alright, perfect. Let's wait like 1 more minute, see if anyone else wants to ask any questions. If not, we'll just end it here. Yes, I think I have, yeah, I think the trickiness was not super high on this AMC. Maybe like the first few questions were, I think the first few questions were actually the most sillyable out of, there's like so many chances for an off by 1 error or something. Like number 1 is the classic off by 1 error problem, right? But like it's on the AMC 10, so there's probably a trick to it. You're not just adding 2 numbers, right? So like your sixth sense should like go off here. Number 4, I guess, is also possible to make it off by 1 error. Number 5 is definitely possible to make such an error. So there's definitely like a lot of situations toward the beginning of the test, I think, that were sillyable. But I think the latter half here is actually very unsillyable. I guess number 23 is possibly like if you added stuff wrong, you would be off by 1. But in this case, all the unit digits are different, so you can do a sanity check. Yes, I noticed there were a lot of questions. Yeah, definitely the last 5 questions were on average way easier than normal. And then what is it? What was I gonna say? There were definitely a lot of questions where you could use answer choices to your advantage. Let me just give you a couple examples of that. Like, for example, let's see. Oh, yeah, this one was also sillyable because you could think that 7 pi is like slightly greater than 22 if you did the multiplication wrong. You can use the answer choices, for example, let's see. Let me give you a good example. I guess number 12 is like one example where you see that 9 is possible, and then 9 is also the smallest possible answer in the list, so you know that you're already right because you found something that works and there's no answer choice less than 9. Another example is number 16, where we figured out that the number of integers is always 2 mod 3, so you always have at least a 50-50 chance on that one. You can also use an answer choices to think about what might you be missing. There's always like that type of question where you have a question. Like this one was kind of in that category, right? You get 1/9, maybe like you only see the small pipe, right? The small example where you have one here, and you get the answer 1/9, but then you see that like, oh, 1 is also an answer. 10/9 is always also an answer. Highly suggests that 1 is also a possible radius or something similar, right? So you want to always look for that situation where you can look for answer choices that maybe challenge your answer. Like there's the classic example of like n is an answer and then so is like n+1, but then all the other answers are like really far away. Like whenever you see that pattern of like two numbers that are really close, chances are that the answer is one of them, right? And furthermore, chances are that like so you already have like a 50-50 chance if that type of answer choice list shows up. And like remember on the 10A, the very last question, number 25, it was like the slither link. You have the grid and you have to make a loop around the ones. If like I got the answer 144 because I missed 2 edge cases, and then I saw the answer 146. I was like, oh, there might be more, but I didn't have time to actually do, the actual like investigation. Oh, there might be like an extra number here, right? That like some other configuration that gives us more cases. But unfortunately, I did not manage time well that test, and I did not end up finding those 2 edge cases. But that was definitely like one of those interesting situations where you can use answer choices to double check your answer and look for additional cases, especially when it's like off by 1 or 2. And then let's see, there's also cases where you can, okay, like take a look at number 11, right? Or not 11, number 10. This is a classic example where you have a parallelogram with unknown sides, and basically it's entirely unspecified. So since the answer has to be the same for like all possible parallelograms in order for this question to work, you just like pick a square, and that just makes everything so much easier. Though I think if you have good technique, that doesn't really matter. It just helps like with like assigning concrete values to stuff, and that also helps you like draw better and make sillies less often, I think. So it's always a good idea to like use a square when we have a parallelogram with no other specifications or constraints, right? Like in this case, there's no other given values other than it's a parallelogram, right? So you can definitely use a lot of tricks with answer choices and with the problem. If it's like vague, you can like make some assumptions that you normally wouldn't be able to, and so on, right? All right. That's basically all the remarks I have on this test. But again, if you have more questions, you can go ahead and ask them now. I'll give you like 1 more minute to look over the test and think about things you want to explain. If not, I'll end the stream at 8:19, or like in 30 seconds. Yeah, I agree. You can do 20. Oh, just search. Like, I don't know if I'm allowed to provide a link, but I mean, it's been a day right here. Like, if you go to the Ivy League Education Center, it has like answer keys, but like I think it's also, oh, it's on. Oh, yeah, that has all the answers and also the questions. So yeah, yep. Oh, that's unfortunate. Yeah, you see the 1/9, but the bigger one is like slightly. Like when it says the sum of stuff, like it kind of suggests that there's more than one. Though I think there are definitely cases where there is only one case, and the sum is it's just like normally the test is not meant to be like deceptive like that. So it's actually, I know in like old years like 1990s, early 2000s that was the case, but I feel like test writers have become a lot more clear, and like people will only write the sum of possible things only if there's like more than one possible answer. So definitely, like, again, those sort of things should raise alarm bells in your head. Like, oh, I should be looking for more than one configuration, maybe two, maybe even three, right? So always be on the lookout for those. Definitely like not missing those edge cases, or like trying not to make sillies is a big part of increasing your score. Not just learning more concepts, or like, so that's a very underrated part of practice that I think all of you should always look to. All right. Thanks everyone for coming. This was the 10B live solve. I got a score of, let me just change it now, 144. Should have been a perfect score. So close. But yeah, everyone makes sillies. All right. I'll see you, everyone.